we want to return to our idea of electron configurations and talk about orbital diagrams. So all of the configurations that we've talked about, we started with standard and then looked at noble gas configuration for electrons, and all of those only show the subshell level, right? 6 electrons can go into a 2p subshell, but we know that the subshells contain orbitals. So what we want to talk about now are some different representations of configurations that give that orbital level insight. Maybe not all the way down into saying that there's an electron in, say, this orbital or that orbital, but still a little more of how electrons are distributed among the orbitals within a given subshell. Our standard or kind of beginning way that we do this is box notation, where the orbitals are going to be represented by boxes, and we're going to use electrons for our arrows. So what that looks like, for example, an S-type subshell, we know only has one orbital, so an S gets one box. P-type subshell has 3 orbitals, so we have 3 boxes, and you'll note they are linked together. They're literally touching. D has 5 boxes, and this would continue so on. Electrons then are going to be represented using arrows. We can have up arrows or down arrows. The directions of these arrows represent that idea of electron spin. Remember that final 4th quantum number, m sub s, can either be plus 1/2, that would be an up spin, or it can be minus 1/2, which is a down spin. So you can have up spins, down spins. You can't have left and right spins for electrons. Let's see what that looks like for some examples. We know H has its configuration is 1s1, a single electron in the 1s subshell. So we're going to write our box for that is 1s, right? We do label it with the full name of the subshell. And then we know the 1 electron that comes from that exponent. So we put an arrow in. That arrow can be up or down. Generally kind of standard, we always use up. But it could be either. It just needs to be an arrow in that box. Helium would be our next most complicated atom. 1s2. We now have 2 electrons. The same 1s subshell is the only thing we have still. So we put an arrow in. When we go to put the second electron, that arrow needs to point down. That's a reflection of the fact that the 2 electrons in a given orbital have to have different spins, right? The reason why each orbital can hold 2 electrons is because you have 2 possible values for that spin quantum number. And so each electron needs to have its own unique set. That's the Pauli exclusion principle. So we have 1 up, 1 down. That will work for that orbital. Lithium, 1s2, 2s1. So we know the 1s subshell is full, so our single orbital, single box, has 2 electrons in it. Whenever we see, this is full right here, 2 electrons, that's going to be 1 up electron and 1 down electron. So then, as we add more subshells, we add more boxes. It's a 2s subshell. It's a S-type, so again, it's only a single box, and we still label it with the 2s. We have 1 electron to put into there, so we just put the 1 arrow. Again, it can be pointing up or down. Standard practice is to use up when it's a single, but either works. Boron, 1s2, 2s2, 2p1. So the 1s, we know that one is full. 2s2, also full. So now when we hit the 2p, this would be the next highest energy. It is partially occupied. There's at least 1 electron in there. When we write it out, we include the entire subshell. So even the empty orbitals are still there as boxes. Even though they're not all going to be filled because we only have 1 electron to put in there, we leave them all just to show that that is a whole subshell. And we put in our single electron, right? That 1 right there is just the 1 right there. And it can go into any box. Usually we use the leftmost box and an up arrow. Carbon. 1s2, 2s2, 2p2. So the beginning, we talked about Aufbau principle, still applies. The 1s2, 2s2, that's going to look exactly like it did for boron because they were filled. But the 2p is going to be a little bit different. Now we have those 2 electrons. So we know the first one can just slot in. So now the question is, where do we put this second electron? We have some flexibility. we have, all sorts. We have different orbitals. We have that same orbital. And how we choose where to do it is we use what's called Hund's rule, which says the most stable arrangement has the most parallel electron spins. What that means is twofold. One, if we have an open orbital, we put the electron into there. So I'm going to put it into one of these open orbitals. And we make sure that the spin, i.e. the direction of the arrow for that second electron, matches the direction for our first electron. So we have an up arrow in this orbital, also need an up arrow in this second orbital, right? We don't put a down arrow into any of the orbitals until we've put as many up arrows as possible. So we can follow this trend. We can fill electrons, we put them in one at a time. And we can see we did, where is it? Boron and carbon right here. So we did the 1, 2 for nitrogen. We again put that next electron into another orbital by itself, and we have them all pointing in the same direction. So for the case of nitrogen, I got 3 electrons all pointing up. So they're all pointing in the same direction. They could all be pointing down. We just want them to all be pointing in the same direction. After we hit nitrogen, once we have one in all 3, when I go to add another electron to oxygen, I'm not going to start using like the 3s over here or something like that. I'm still going to fill that subshell. It's not worth it to start going to higher energy subshells. Instead, I just start pairing things up. So I get 1 pair. For fluorine, I need to make a 2nd pair. And for neon, I make everything paired up. So I got everything paired up nice and good. So everything is good to go. I have everything filled up, and now with neon, with that 10th electron, now the 2p is full. If I'm going to add an 11th electron, that's where I would start going to a new box. I would go up to the next highest subshell, 3s, start putting electrons and following those rules. Let's look at some more examples of these box diagrams. So right at the box diagram, electron configuration of the valence electrons. Note, I'm only asking for the valence electrons here. As you may have noted, or kind of figured out, these get really bulky really fast. So in order to save space, we're only going to look at the valence electrons for these. When I want to go about looking at this, the question is going to be, well, what are those valence electrons, right? When we were trying to figure out the box diagram for helium, hydrogen, we always started with the electron configuration. So what are the valence electrons for these elements? We can use the periodic table, what subshells are occupied by those valence electrons, and then fill them in using the Aufbau principle, along with some of these new ideas, Pauli exclusion principle, how do you put the spins, the Hund's rule kind of stuff. All right, so selenium, Se, right there on the periodic table. That is in the P block, right? We know that this whole thing over here is in the P block. We know it is in the 1, 2, 3, 4th column of the P block. So that is 4p electrons, and it's in the 4th period. So 4p4 is how it's going to end. So there are 6 valence electrons, 4p4, and 2 in the 4s. So we are looking for the valence electrons to fill those. And so that means those are the boxes we need. We need a box for 4s, that's an s-type subshell, so it only has 1 orbital. 4p is p-type subshell, so it has 3. When we go to put the electrons, 4s is full, so it gets an up and a down arrow. We want to be sure any single box, if it's going to have 2 electrons, they need to have opposite spins. Then when it comes to putting electrons in the 4p, we know we start, 1 goes in, the next one goes in. We want to make sure the spins are pointing in the same direction. Keep going across. We need to get 4 total. The max you can have pointing in the same direction is 3. So the 4th one has to pair opposite. So it's not impossible to pair up. You just wait until you have to pair up electrons. PD, palladium. That is in my D block. I can see if I look right here that there are 10 valence electrons. I'm in period 5, so I know this is going to be the 5s. I have 2 in there, and then this is going to be 4d. I have 1, 2, 3, 4, 5, 6, 7, 8 of those. So 5s is going to have 2, and the 4d is going to have 8. All right, so that means those are the boxes I need to put. Those are the subshells that have any electrons in them that are valence. So those are the ones I need to fill. We want to remember that these D-type subshells have 5 orbitals, so they get 5 boxes. The 5s, once again, is up and down. It's full. And then the 4D, we're putting in 8. Well, we work our way one at a time. We keep going, pointing in the same direction as long as we can. Once we hit 5, that's the maximum for a D-type subshell. So we need to circle back. We need 8 total. We were at 5, 6, 7, 8. And so we wait to pair them up until we need to, but once we have hit that point, then we just keep pairing them up. And you'll note we still have the maximum number of parallel spins. I have 2 parallel spins here. That's the maximum that I could possibly have out of these 8. And so that follows Hund's rule. If we would need to add more, we would keep pairing them up, but we can keep them parallel as we need to. Now we want to look at some slightly different examples where we look at just kind of parts of box diagrams and see what's wrong with them. So the first one, and we can see we got the 1s2, 2s2, 2p2. So we want to think about, is this filled correctly? Are these arrows drawn in the right places, right directions, all sorts of ideas. And so the problem we can see right here is this right here. We have the 2p2, which is fine, but the problem is that those 2 shouldn't be paired until we need to. This violates Hund's rule, right? That those parallel spins, that when you add the second electron, it should go into the other orbital, not into the same orbital. If we look at our second example, I have the 1s and the 2s, my 2p is empty. And this one is wrong because this one violates the Aufbau principle, right? We should be filling our subshells before moving on to the next one. Right, this would be, if we look at it, if we think about writing the notation, it'd be 1s1, 2s1. Right, we've put an electron into the 2s orbital, 2s subshell, before the 1s subshell is full, and that violates the Aufbau principle. Right, we can't do that. We need to fill up the s. We don't want to have this thing right here. It should instead be opposite spin in the 1s. Hund's rule does not go between. It's not like we want to make parallel spins between subshells. Hund's rule only applies within a subshell, like we saw over here with the 2p. All right, this bottom right one now. What do we switch to? Let's do green. So we got 1s2, 2s2, 2p1. This may look a little weird, but totally acceptable. You have that middle, that single electron, the 2p in the middle diagram, middle orbital. That's fine. These orbitals are just, this isn't a real orbital, it's just a box. So you can put it wherever it is. The most important thing is that it's in the right subshell energy-wise, right? Are you doing the Aufbau principle? And then are you not violating Hund's rule? Do you have parallel spins? Because there's, the 1 electron in there, that's going to be totally okay. There's no rule to potentially violate. Bottom right now, so I have 1s and some electrons in the 2s, and then the 2p is empty. This is wrong because you're violating the Pauli exclusion principle. You cannot have more than 2 electrons in a single orbital. And if we look at how this 2s is written, that is a packed house. You can't have 3 electrons in there. You cannot have an up and 2 up arrows in the same orbital, the same box, like you have in the 2s. They have to be a max of 2 electrons, and they have to have opposite direction spins. Okay, looking for more questions on participation 623. See you in the next video.